Hello again. My name is Simon Timpley from the International Food Safety and Quality Network. Welcome to edition 92 of the Food Safety Fridays webinar program. It's good to be back after a short break. Today's focus is on compressed air testing, and the title of the webinar is Passing Your Compressed Air Analysis Tips and Troubleshooting for Successful Compliance, and that's with Matthew DeVay, Quality Assurance Director at Trace LLC. Now, Trace LLC are one of our kind sponsors and the organizations that support the Food Safety Fridays webinar program, helping to bring you free education and a certificate of attendance that you can put in your personal development file and show to those pesky auditors when they ask you how you're keeping up to date with things. So yeah, the sponsors of this program: Trace Analytics, Safe Food 360, DNV GL Business Assurance, Metal of Toledo, and AIB International. So it's good to be back. At this point, I'd like to introduce you to Matt DeVay, if you're there, Matt. If you can switch your... How are you doing, Matt?
I'm doing well. How are you, Simon?
Good. This is your first time with us. Yep. So we're looking forward to it. And you're dialing in from
Austin, Texas.
And the weather is?
The weather's it's actually pretty beautiful right now.
Very nice.
About a high of 78. Gonna be nice and sunny.
Lovely.
Good outdoor.
And actually, as I look out the window, the sky is blue and the sun is shining. So let's hope the sun shines on us today and we don't have any technical gremlins. If you can get your slides ready, Matt, I'll just tell the audience about next week. Ladies and gents, I'm going to put in the sidebar next week. It's actually it's a training course next week, Practical HACCP. So if you want to click the blue button, it'll open a new window. You can have a look later. That's next week's training. It's a 4-hour training course. But you can respond to emails as well. I'll be back for the Q&A later. And we hope you have a good webinar, and hope you enjoy it. Nice to have you all with us again. You can put your slides on whenever you're ready, Matt. Okay, ready to roll. I'll hand you over to Matt, and I'll be back later.
All right. Thank you, Simon. So my name is Matt DeVay. I work for Trace Analytics. We specialize in compressed gas testing. Been working in the chemical industry for about 10 years now. I've been doing QA and chemical testing basically that entire time. My degree is in chemistry from Texas A&M. Specialize in GCMS. I'm the quality director here at Trace, which basically means that I try to make sure things don't break and then fix them when I do, or when they do. Naturally, a big part of this is regularly working with customers to kind of help them figure out where things might be going wrong for them. So essentially what we're going to talk about today, a lot of cases, typically your compressed gas will be all right, but you might still fail. So we're going to kind of isolate those problems where those happen and help eliminate inaccuracies in your results. So these are just a few of the common regulatory bodies that you might have to adhere to. All of them have kind of slightly different compliance requirements. So always just know who you're working with and what they need out of you. So most standards require manufacturers to develop their own risk analyses and evaluate their systems accordingly. Once again, know who you have to be compliant to and what that entails. In the case of compressed air, most manufacturing applications use ISO 8573 as a guide, but you don't necessarily need to follow it exactly. It's definitely a good place to start, though. And ISO 8573 itself has no real advice, just the methods and the specification limits that they outline. And then depending on your application, you may need to consider things outside of ISO 8573, like compositional purities, if you're using something like nitrogen for inert fills or CO2 for carbonation. So just real quick, compressed air systems. You need to know the capabilities and installation of your system. Most systems these days have a pre-filter and a compressor where air comes in and is compressed to higher pressure. You have first stage treatment, which is primarily for condensates such as water and oil. The air typically goes to storage, not always. Upon demand, air will flow out of storage and typically goes through a few more condensate and organic vapor filtration. And then it goes to the drying step. A lot of you probably use refrigerated dryers. Some of you might have emulsives or desiccants. But these both are the same in that they remove water out of the air. After drying, typically there's a first pass particulate filter that can remove anything that might be introduced in the drying step, particularly if you've got desiccants. And then finally the air ends up at the point of use. And at your point of use, you might have quite a bit more filtration. Another desiccant filter to remove water, a condensate filter to remove oil and water, and then almost always some kind of extra particulate filtration as well. So some characteristics of a compressed air system. One thing to remember is that any compressed air system is dynamic. Your compressed air will experience changes over time, and it will exhibit both short-term and long-term trends. Quality of intake air, system demand, system age, system materials, how it's mounted, the order that you have filters in, they'll all have an influence on how your system performs. So what do we commonly test? Well, particulate content, water content, oil content, both aerosols and vapors, and bioburden or microbial content. You may also need to check your purity for composition, as mentioned before, for CO2 or nitrogen if you use those kind of applications. So here's a pretty intimidating chart. This is the class chart for ISO 8573. This kind of outlines, if you pick and choose classes to build your system around, these are the limits for those classes. So if you look across the top, you've got particles, water, and oil. Across the side, you've got the purity class itself, and then in the cells where the columns and the rows meet, those are the limits that you have to achieve if you want to say your system is meeting a particular class. You have no obligation to say, okay, well, I want a class 2 for particles. That doesn't mean you also need class 2 for water and oil. So you can pick and choose by section which classes you want. So you can say 2 for particles, 4 for water, 2 for oil, which is a fairly common specification that I see for direct contact air for food. You can do things like 442, which is a fairly common one that I see for indirect contact. You also don't necessarily have any obligation to follow the chart exactly. So if you do a risk analysis and it says, okay, well, we might want a class 3 for particles and class 4 for water, but oil, really what we need is 2.5 milligrams per cubic meter. You can make that specification for yourself and have it tested. So part of troubleshooting is knowing how you're making measurements. Different measurement types are going to lead to different kinds of troubleshooting steps. And we're going to kind of go through the technologies and the pros and cons of each one through the next few slides. So particles. One of the most common and robust ways to measure particles are laser particle counters, or LPCs. These measure your process gas directly while it is flowing with minimal interference. Basically, you hook it up, open the valve, turn it on, and you let it do its thing. They sample for a fixed amount of time, typically about a minute, but you can adjust that if you need to. Air will flow through the thing for a minute, it'll count for a minute, it'll turn off for a minute, then it'll count again for a minute, typically so on and so forth until you tell it to stop. The results that you get out of an LPC are very close to a direct representation of the system at that time or at that moment. But remember, going back a few slides, these systems are dynamic. That may or may not actually be how your system's performing over a longer period of time or as a reasonable average. They are highly accurate instruments. They can count particles down to 0.1 micron. So why wouldn't you use one? Well, as mentioned, you're not necessarily getting anything more than a snapshot of your system for a very short window. Not necessarily a good representation of average performance. They tend to have small sampling volumes, which kind of feeds into that. They're heavy, bulky, kind of a pain in the butt to move around and ship. They're normally used for ambient sampling, so you almost always need some kind of additional equipment to make it suitable for compressed air. And they are really expensive instruments. There's also some hidden cost of operation in that they require regular calibration. And that's something that people don't necessarily consider is what is it going to cost for me to ship this thing and get it calibrated on any kind of regular basis. So next up is a condensation nucleation counter. These are very similar to LPCs aside from the actual technology of counting. They work by condensing vapor on particles to make them easier for an optical sensor to see. So essentially they operate by making particles bigger in a way. The problem with these is that you can't get good sizing out of them without extra instrumentation. So you need what's called a differential mobility analyzer to be able to bucket your particles into different classes. The cool thing about these is that if you have the need to see particles below 0.1 micron, this is the only way that you can do it. And then all those same caveats as far as why you wouldn't use it for apply. They're heavy, they're expensive. These also have consumables, so you need some kind of liquid to vaporize. They require calibration. And one other caveat about this guy is that works best at higher particle concentrations. So if you're trying to achieve lower classes, they lose accuracy at lower concentrations. Membrane microscopy is another way that people check for particles. This one's a little bit different. You're not getting a real-time measurement anymore. Now you're kind of getting an aggregate measurement, and you're dividing by the volume of gas that's flowing through the membrane. Why would you choose this over other ones? It's not particularly expensive. You get a really good representation of your system over a longer period of time. Remember, these systems are dynamic, and you're kind of capturing more information about the system over an averaged time. Why wouldn't you want to do it? Well, if you really need to see particles lower than 0.5 micron, it's basically impossible to do with optical microscopy. The limits of diffraction, that pesky thing about physics is that you can't see things smaller than the wavelength of light, and 0.5 microns happens to be about that cutoff. So you're kind of limited in how small you can go. The other thing about membrane counting is it collects particles not just while it's connected to the system, but basically from the time that you unseal the cap on the membrane housing until the time that you put that cap back on. So if you're working in a mill of some kind and you've got a lot of particulate in the air, or if you're using valves, ball valves in particular can be not a very good match for membrane microscopy. It's going to measure your technique and your equipment as well as your air. And so that's a common pitfall that you can have with these. The other thing about them is if you've got stricter classes that you need to meet, if you're going to try to meet an ISO class 1, expect to have that membrane hooked up to your system for quite a while. So why do these tests fail? So things that you can control that may make this fail are obviously old and ineffective filtration. Leaks are always a big problem. Remember, air that's moving or fluids that are moving have lower pressure. So if they're moving fairly quickly and you've got unrestricted flow through the system, full flow sampling, you're going to have these kind of suction, siphon, Venturi type effects that have opportunities to pull in particles from the outside through the leak into the sampling media. Sampling point contamination. This can be environmental contamination, construction material contamination, things like black iron, soft rubber. These guys shed particles fairly well. Avoid them for use. Avoid them in your point of use. You definitely don't want to use these materials if you need to meet stricter particle classes. Poor choice of fittings, units, and valves. So ball valves in particular are problematic. They have a lot of surface area. They have a lot of opportunity to collect contamination. Every time you turn that valve, you might be releasing some more of that into your system. Conical fittings also kind of have some problems associated with them in that they're friction-based fittings, and they have a lot of surface area to hold contamination. Avoid metals of different hardness. This is a pretty common one. You see people with aluminum systems and they're using a steel sampling point. You'll see people using copper piping, which is not necessarily a bad material to choose. But then if you're going to hook up a 1/4 inch NPT test kit, you've got to make the transition between copper and steel. So anytime that you have metals of differing hardness, the softer metal will generate particles through vibration and friction against the harder metal. The other thing is all of these X tend to feed on each other. So if you've got a ball valve and then multiple different types of metal in front of it, you're just kind of exacerbating the problem. So definitely think about your point of use and how you're setting that up. All right, water content. So one of the most common ways to measure water is electrochemical sensors. These detect water vapor by using materials whose resistivity or capacitance change in the presence of water vapor. They tend to be fairly accurate. They tend to be pretty easy to install. The problems are they have very long equilibration times. They really like water. And so once they have water on the sensor, it takes a very long time to flush that water off the sensor and have it reach equilibrium. So they tend to be mostly used for permanent installations. The other thing about them, they're kind of expensive and you pay for dew point limits. So if you want to reach, say, a class 2, which would be minus 40 Celsius, you're going to pay a lot more money for a dew point sensor, electrochemical dew point sensor that can go that low. They also require calibration. So keep in mind that's a hidden cost that you're going to have to deal with, and something that's going to essentially shut you down on that particular point of use until you can get it calibrated. One more thing to have in line for an audit. All right, chilled mirrors. So this is a dew point hygrometer, chilled mirror type. These work by having a mirror that gets very cold as the air flows past it. And as the mirror chills, it will condense water vapor out of the airstream. And then it's got a light beam that bounces off the mirror to a sensor, and the sensor will detect when the mirror is fogged. So you know when the mirror fogs, you know what temperature that is. That also happens to correspond to your dew point. These are pretty much the gold standard for really accurate water vapor measurement. But they've got a lot of those same drawbacks of electrochemicals. They take a long time to equilibrate. So you hook it up and it's probably going to be a good 30 or 40 minutes before you'll get a stable reading. Particularly for lower dew points. They have a lot of parts that have to be properly aligned for it to work. So they don't really tolerate being moved around or bumped that much. So they tend to mostly live in labs on a shelf where they don't really have to move around. So makes them kind of delicate instruments. And then bulky, obviously, and then if you're trying to reach lower dew points, typically you need a second chiller unit to get that mirror down to colder temperatures, and that's an even bigger and bulkier piece of equipment than the dew point hygrometer itself. One of the most common ways to detect water vapor in gas streams are detector tubes. So these work with a chemical stain. It's a chemical reagent that progressively changes color as water vapor in the air interacts with the media. They're cheap, they're fast, super easy, but they do have a few drawbacks. They're definitely significantly less accurate than the previous two methods, though they tend to be fairly suitable for most cases. The reading of the tube has a subjective element to it, which kind of feeds into that inaccuracy of the tube. They use a kind of non-linear scale. And so when you're reading a mark between 80 and 100 on the tube, you don't really know if that's 90 or 88 or 92. They can be a little challenging to get an accurate reading off of. And then, of course, if you're working in a plant, food facility, typically a lot of these places don't allow glass in them, particularly if you're working in a bottling plant. Presence of broken glass might shut down your line, and these you have to break glass to use them. So it may or may not be suitable for your application. All right, so why do these fail? Contamination is probably the #1 reason why a water vapor test will fail. A very small amount of water will make a very big change in your dew point, particularly at stricter classes. So if you're trying to get a class 1 or a class 2, I mean, for instance, 1 ppm at class 2, will raise your dew point by 10 degrees. It's a very tiny amount of water that has a very big effect on your reading. A fingerprint on your equipment can retain enough water to make the difference between passing and failing. Materials, these can lead to contamination as well. If you're using polymer tubing and you need to try to hit a stricter dew point, you're going to have some pretty bad luck with that. Most tubing is permeable to water. There's not a polymer out there that is completely impervious to water. Even PTFE has a fairly high rate of permeability to water. And I say high rate, it's in the parts per million kind of range, but as you can see, a single part per million makes a big difference with this. Leaks, obviously, if you're pulling in water vapor, if you're in a humid area, a leak will cause you a lot of problems. Old or ineffective filtration, you're going to see this one again and again and again. Not all filters are created equally. And if you're depending on point of use desiccant filters, make sure that you're checking those and changing them out on at least the manufacturer's recommended cycle, if not preferably more frequently than that. The placement of traps. If you've got traps before your point of use or your sampling point, you're going to have humidity in your system at that point. And then also the orientation of your piping. If water's collecting, if you're using a refrigerated dryer and you're not getting all the humidity out, you're going to have points where your piping is in downward or vertical or sloping downward orientations where water will pool and collect and increase the humidity in that part of your system. All right, on to oil aerosol. So there's a few different ways to collect these as well. Membrane extraction is probably the most common. You've got a membrane media in there, typically some kind of either polymer media or glass fiber. And oil aerosol droplets just collect on it. You pull the filter back out. You either extract it or weigh by difference. You can get as fancy as doing an IR spectra on the extract, and then you know how much oil aerosol is in there. So this one's pretty simple. It's pretty robust. Pretty easy to use, inexpensive, fairly accurate. Problems with it, particles can interfere. So if you're using any kind of polymer O-rings, if you've got polymer tubing further up the line, if you're just using rubber tubing somewhere in there or nylon tubing, those particles are slightly soluble in the solvents that you use to extract, and it will give you falsely high results because of that. So you've got this filter disc with, say, red rubber particles on it or nylon particles on it, and you extract with pentane. There's things in that red rubber that are going to come through with that pentane, and that rubber's not oil aerosol, but it's going to get counted as oil aerosol. The other thing is that the sampling time can be long, kind of like with membrane counting for particles, because the limit of detection is based on the volume of air that goes through the membrane. A lot of people really like to use detector tubes to measure oil content, and we'll come back to these when we see oil vapor as well. It's essentially the same tube that measures both, but there's a lot of caveats. They are advantageous in that they're inexpensive and fast, but some of the problems, they don't see everything that might be oil. Typically, these have a few target compounds that they're calibrated against, and so. What if you're using a silicone oil? A lot of these don't respond very well to silicone oil. Sometimes these things respond really well to things that are only minor components of your oil vapors or oil aerosols. It can't differentiate between oil vapor and oil aerosol. So that can be a problem depending on what you need. And they've got a lot of the same accuracy problems that water vapor tubes do. But when you compound that with the fact that it's not necessarily seeing everything you need it to see, or biased towards certain things that you may have, it just compounds that inaccuracy even more. The water tubes are kind of advantageous to the oil vapor tubes in that they're only looking for one thing. The oil detector tubes are trying to detect all the things, and it's not very good at that. Another common oil aerosol device is an impactor. These are interesting things in that oil droplets will impact that membrane at the end. There's a series of dots on the end, a row of 5 open circles and a row of five dots. And what you're doing is you're watching it bleed. As oil aerosol impacts it, the ink is soluble in the oil, and it starts to kind of smear around a little bit. And you're supposed to make your reading based on how much that ink smears. Well, that's kind of a weird thing to make a reading on, and so the accuracy of these things is very subjective. The other thing is they have very poor limits of detection. They're not able to see oil at levels lower than about 2 milligrams per cubic meter. So if you have stricter classes than that, then these are not going to be appropriate for you. So why do aerosol tests fail? Well, there's that old and ineffective filtration again. Change your filters, guys. The other thing is not all filters are created equal, so go with a brand you trust. I'm not going to drop any names here, but definitely do your research on what's a good filter. Definitely your placement of your filters in your condensate trap, same kind of thing with water. If your condensate traps are closer to your point of use, you're more likely to get oil aerosols coming through. Materials, if you're using a lot of polymer, oil aerosol loves to cling to polymers, and it becomes a point of continual low-level contamination. Just be careful with that kind of thing. Any devices that you have that may need to be lubricated, if you've got valves, certain gauges, certain measuring devices, quick releases that require lubrication, any of that kind of stuff, just make sure that you've got a way to clean that, because all of that stuff will end up in your aerosol analysis. And that same vertical or downward orientation of sampling port applies. You'll get that oil that will start to pool and collect in those areas. So avoid that prior to your point of use or sampling point. All right, oil vapor. So these are the vaporous components. Oil aerosol is liquid in tiny droplet form. Oil vapor is in gas form. So this is one of the more common thing that you'll see in some high-end installations is inline instrumentation. These are typically either flame ionization detectors or infrared detectors. Flame ionization detector works by having a little flame, and then it measures changes in the flame as vapors move across it and burn. Infrared uses infrared absorbance to determine the presence of oil vapors. They are fast, they're real time. You get results or information as the gas is flowing through. But they're almost always permanent installs. They're not something that you can carry around from sampling point to sampling point very easily. Other things about them, they're really expensive. They do also require outside calibrations. So with these, since it's a permanent install, you've got to now pay someone to come on site to maintain and calibrate your really expensive device. And they don't really give universal results. So depending on what your individual components of your oil vapor may be, some of them are going to give better responses and indicate a presence of more vapor than other compounds. So your more common mineral oil type constituents may give you very high responses. Your more common silicone type oils are going to give you lower responses. So the accuracy is kind of dependent on interpretation in that case. And they are hugely expensive. Expect to spend a lot of money if you're going to install these at all your points of use. Detector tubes, these are basically exactly the same tubes as you use for oil aerosol. All the same caveats apply. I don't think we need to go through this again, I don't think. And then desorption tubes. So these are probably one of the better compromises as far as technology you might use to do oil vapor measurement. They're fairly inexpensive. They work with sorbent material that trap the hydrocarbon vapors. Typically that sorbent material is activated charcoal. And they essentially work on the same principles as your activated charcoal filters. They're going to trap those hydrocarbons. When they're done, you're going to send it off to a lab. They're going to extract the hydrocarbons off the charcoal using some kind of solvent like carbon disulfide. And then they're going to analyze it on some kind of instrumentation, typically GCMS, gas chromatography with mass spec, or GCFID. Those tend to be the more common ones. The cool thing about this is that not only are you getting pretty accurate representations of what your oil vapor actually is, but you can also get it characterized and know, exactly what's contaminating your system. So this tends to be a fairly robust and reasonable compromise to having like inline instrumentation. One other thing you need to be aware about, though, is if you've got high levels of oil vapors in your system, very likely that you can overload the tube, and you're going to get a result back that you can't really use in the face of an audit. So once again, why these things fail, filtration, you're just going to keep seeing that because that's a really big thing. Sampling point and or intake contamination tends to be also a very common thing. If you're using solvents to clean your point of use or your sampling port, oil vapor testing is going to see that. Spilled fuel or solvents in your facility, oil vapor is probably going to see that too. The most common thing that I see in oil vapor testing, limonene and pinene, which are lemon scents and pine scents respectively. And these are almost always artifacts of cleaning solvents you might be using. So if you're using some kind of cleaning product, pine sol on the floors, if you're using some kind of lemon cleaner on your tables or on the sampling point itself, your oil vapor test is surprisingly enough going to pick that up. All right, moving right along, a lot of you probably are fairly familiar with microbial testing, or at least the need for it. There's two different types of testing that can be done for microbial, qualitative and quantitative. Qualitative is looking at what the microbes actually are. Quantitative is looking at how many microbes you have in your system. So if you need quantitative, these microbial impaction samplers, these are going to be the ones that are most relevant to you. Typically, you're going to put a Petri dish of some kind, some particular size that matches your sampling unit. It's going to have some kind of agar media on it. The most common media is tryptic soy agar, or TSA. This is a really nice general purpose media that'll grow just about anything. But if you need to get really specific and you need to look specifically for something like Listeria or Salmonella or Shigella, you can get medias that are specific to those that'll only grow those particular pathogens. These work typically with either a slit or a diffuser. They blow the air through the system, the particles embed into the agar, and then the agar comes back to the lab for incubation and running. Fairly simple. They can be both quantitative and qualitative depending on the capabilities of the lab that you send it to. A lot of you may or may not be familiar with what's sometimes referred to as the spray and pray method. This is a qualitative only thing where people will commonly take a Petri dish, put it in a sterile bag, and then just blow air into the bag. The thing about this method is that it is qualitative only. There are even some devices that kind of enable this, so you're no longer using the bag. Once again, not going to name names, but there's a couple fairly popular ones out there. The sampling is typically a little bit cheaper. The device that you're using is a lot less expensive. But you got to keep in mind the only information that you can get out of this that's particularly useful is what you have. So if your specifications require you to know how many microbes or how many viable particles you have in your gas, this is not going to be suitable for that. The other thing is this has got a fairly high potential for contamination, but it is really useful if you need to know whether or not you've got Salmonella or Listeria in your lines. So why it fails? Well, once again, that filtration thing, that just keeps popping up. The only place in a compressed air system where microbes really like to grow tends to be in your condensate and coalescing filters. So your condensate traps, your coalescing traps and filters, those are the only places that are particularly habitable for microbes in your system. So just make sure you've got good particulate filters beyond that. Environmental contamination and poor technique are going to be the most probable causes of inadvertent failures. You have to be very careful handling the media. If you touch it with your bare hands, or even if you're wearing gloves and your gloves are dirty, if you sneeze on it, drop it, leave it open too long, you're probably going to get growth on your plate. Your skin has all types of microbes on it that will happily grow on tryptic soy agar. Same for your mouth, same for your floor, your shoes. Basically everything in your environment has something on it that will grow in that agar. So handle those plates very carefully. Aseptic technique. If you don't know it, learn it. Fun little aside, I have a friend who works in the ultra pure water department for Samsung in one of their computer chip foundries. And they can remove all of the impurities in the water, all the tiny little particles, trace minerals. They get water that is like 99.999999% pure. But they continuously have problems with algae and bacteria in their systems since they can't treat the water with chlorine. They have no idea how it gets through their filters, and they still have to stop fab and clean all the pipes on a pretty regular basis because of it. Point being, microbes are everywhere and they get into everything. So be really careful with those plates. All right, so we're about wrapping up here. We're just going to kind of go through some best practices. Your piping and tubing, particularly at point of use or sampling points, should always try to be horizontal or slanted upwards so that you don't have liquid condensates dripping down. Use non-porous, smooth, non-permeable materials where you can. Definitely avoid connections using metals of different hardness. If you do, try to go for face seal or solder joints instead of conical threads. Always ensure the proper application of your tape, dope, and solder. Those kinds of things, particularly, I can't count the number of times I see Teflon tape on a microscopy membrane. If you gotta use ball valves, PTFE or PFA material, they tend to be pretty friction-free. They don't shed particles very easily. They require less lubrication, makes them less likely to become contaminated. Particularly on your point of use or your sampling points, avoid conical thread fittings if you can. Go for face sealing or compression or sanitary type fittings if you can. Avoid materials that can corrode or deteriorate, like black iron or rubber. One of my first days on the job here, I got a picture of a sampling point, and the entire thing was probably 20 or 30-year-old rusting out black iron, and we're failing our particles. Well, that's probably because you're using rusting black iron as your point of use material. Replace your filtration more frequently than indicated. You don't want to wait until it's a problem to replace these filters. And spend a little bit extra money on that filter. You're going to save yourself a lot of headache further down the line. Always clean your sampling apparatus, your test kits, your sampling points, and flush your system before you take a sample. A lot of these problems can be avoided if you just let that system run at full flow for a good 10 or 15 minutes before you take a sample. As mentioned before, compression fittings, face sealing cylindrical threads, these are going to be your go-to if you're trying to avoid contamination in your unions and fittings. And then use appropriate and high-quality sampling point filtration. I mean, you saw it over and over again in the slides. Old or ineffective filtration is always going to be the #1 thing that will give you problems. Your system can be century-old black iron piping, all types of polymer tubing everywhere, and so long as your sampling point filtration and materials are appropriate, you're pretty likely to pass your testing. All right, that's it. Guess we can open up for questions.
Yeah, super. Oh, my voice. Yeah, that's great, that, Matthew. Lots of great information. I'm sure the audience will agree. A fantastic overview of compressed air testing. Could you just stop sharing the slides now, and then we can come on webcam for the Q&A? Cheers. Right, yeah, we do have a couple of questions. So if you do have a question, attendees, type it in now. We've got some time to pick up on that. But yeah, Stephen Ruggiero, let's start off with his question. How to sanitize airlines? Do you have any?
So are we talking about airlines that are further back in the system, or airlines that are closer to your point of use, or the whole 9 yards?
I imagine that the higher the risk would be nearer to the point of use, I imagine.
Yep. So sanitizing airlines is kind of not that easy as far as the main lines of your system. But if you've got good, effective particulate filtration, you don't really need to worry too much about sanitizing them. A couple things you can do. There's options of like flushing with isopropyl alcohol. One of the easiest things that you can do is 70% IPA. IPA is isopropyl alcohol. You definitely want at least 70%. If there's a way for you to get in from the filter side and flush from that side and then just flush air through your system, that tends to be the best way to go. The thing I would recommend is monitoring your airlines for microbial content. If you don't have much microbial content, write your risk analysis around that kind of frequency basis. So if you're not really seeing microbial content in your airlines at all, you definitely don't need to do it as often as you would if you were seeing it, right? But 70% IPA is kind of the easiest way to do it. You can use bleach, you can use other chemicals, but then you run the risk of contaminating your products with those chemicals. The good thing about 70% IPA, it evaporates very quickly. It's lower risk of contamination of your product.
Okay, super. Right, next one, Jenny, and she is asking, what device can be used to sample compressed air for micro testing?
So there's quite a few out there at this point. We use what's called a Pinocchio sampler made by SAS, but there's a lot of different options for that. I say a lot. There's at least 4 or 5 different options for that. We rent them out, or you have the option of buying it yourself. Most of the places that do microbial sampling have sampling devices available for you to use. Definitely, SAS is the one. Like I said, SAS is the one we use. SAS Pinocchio too. Trying to think of the other. Do you remember any of the other companies that make these things? I wish Maria were up here. They're all very similar to each other in the way they operate. They tend to be made out of stainless steel. They're easily cleaned, but it's a purpose-built thing that you can typically get from the place that's doing your testing, the lab that's doing the testing.
Okay, that's great. Jenny asking further, is there a specific sampling time for micro test and also the sampling time for microbial test of TPC or yeast stroke mold different?
Sampling time's the same for both. And I want to say ours is for 10 minutes. I don't have that document sitting right in front of me. The sampling time's not particularly long for micro test, typically speaking. It's a pretty sensitive test. If it's going to grow, it's going to grow. So microbials tend to not be too big of a concern as far as test time is concerned. And yeah, like I said, it's the same test, same time for total plate counts and yeast mold differentiations.
Okay, Suzanne, are you familiar with CAM2 detection kit by Parker Balston? If so, what are your thoughts on using this unit?
So I am familiar with the CAM2. I wasn't going to mention it in the slides, but since you asked, CAM2 is a really cool device if you need qualitative information. You cannot get good quantitative information from a CAM2. So if you need to know if you have a specific pathogen in your system or a specific microbe in your system, the CAM2 is a really good and really inexpensive way of doing that. But if you need plate counts, the CAM2 is not going to be appropriate for your needs. It's essentially a standardized version of a spray and pray type method.
Okay. Next one, Juan. For food industry, is SS Series 300 for the air compressed system piping? Is that stainless steel?
Yeah, I'm assuming stainless steel 300 series, like 316 or 304. Is that a?
I think is he asking is that appropriate for?
Yeah, absolutely. Highly recommended, actually. Stainless steel is kind of one of the best materials that you can do for your compressed air system piping. The problem is it's not necessarily a very cost-effective way of going about it because it's very expensive. Also very heavy. There's a lot of engineering that goes into installing a stainless steel system. It's difficult to work with, not easy to cut, requires heavier bracketing and heavier mounting, and the material itself is very expensive. But if you have the wherewithal to do it, definitely do it. It will last forever. It will be clean, easy to work with. Once it's installed, you're good for a very long time. So I'd say it's a worthwhile investment.
I suppose it depends also the extent of the pipe, and if it's just a small amount of pipe in a short distance from the, then yeah, it might be cost effective then, possibly.
Yep, absolutely.
Okay. Christy, if you already do air sampling with agar plates, will that system work?
I need a little more clarification on that, I guess. Will that system work for total plate counts? I mean, I don't really know. I don't have enough information to go on here.
Okay, maybe Christy, if you could expand on your question, then we'll might be able to answer that. Pretty Pradhan, for microbial compressed air sample, once you maintain the flow of 100 litres per minute and you get the sample and try to get sample in another spot, do you have to get that flow rate again?
So if you can get 100 mils per minute, that's great because it allows you to sample for the same time on each point. But what's really important is the volume of air that's going across your plate. Typically, you're sampling to a certain volume, which might be 1,000 liters, cubic meter, basically. So you don't necessarily need the same flow at every point, but you do need the same volume to get consistent results. Does that make sense?
Yes, I think so. Yeah. Okay, David may have missed it in the presentation, but from your experience in system failure, does food grade oil need to be should be mandatory?
So that's kind of up to y'all. That's part of your risk analysis. I would always recommend in a food facility using food grade components. It kind of hedges you against system failures. Most of the time, particularly with oil and oil aerosol, you don't typically see a lot of it at the point of use regardless. But I would definitely recommend using food grade oil. I can't speak to yes or no specifically, but it's definitely something that in your risk analysis, you should probably come to that conclusion.
Okay, thank you. And which one are we on now? Susie. Is there a document that tells me the time required for microsampling?
Yeah, and that's going to depend on the lab. They're going to say, okay, we'll sample for this amount of time or that amount of time. If you're doing your sampling in-house, then you kind of just need to do the calculations yourself. I think we set up our sampling time so that it's exactly a cubic meter that's flowing across the plate, which makes the calculations further down the line super easy. But if you're doing it from a lab, they'll give you the instructions for sampling most of the time. And if you're doing it in-house, then you just need a microbiologist that'll help you set that up. But as far as if you're going to order sampling from us or even from another lab, absolutely there will be a document that tells you recommended times and flow rates.
Okay, next one, Irina. We use compressed air to eliminate the defective burgers from the line. We collect that air with the air collection machine and test it in the house lab. Is this method effective? Some locations are difficult to sample.
So, yeah, sampling is always problematic. I was just right before I took this webinar, or right before I came onto this webinar, I was looking at a collection point that was going to be majorly challenging to do. As far as testing in-house in your lab, that's going to depend on the requirements of your auditor, your compliance. They may require that your in-house lab be accredited. They may require audits of the information in your in-house lab. And that's going to kind of be dependent on how your in-house lab is set up. If your in-house lab is set up to be really robust, then you're going to be good to go. If it's accredited, even better. As far as sampling locations, sometimes you just got to do some acrobatics. And that's all about your hazard analysis. If it's a critical control point under your risk analysis, you got to sample it. You got to find a way. And sometimes you got to make a compromise, and you've got to use some polymer tubing or flexible tubing to get to that sampling point. That can be taken into account with your risk analysis, though. You can make the justification of saying, hey, maybe we need a less strict requirement for the sampling point because of the circumstances of sampling, because sampling is part of your testing. Yeah. So it doesn't exist in a vacuum.
Okay. Next, Juan. What is the correct air pressure for testing APC and YM?
There's not really a pressure that's appropriate, but there are a range of flow rates that you kind of want to adhere to. When we're talking about sampling and testing for compressed air analysis, pressure is relevant mostly only to dew point, because if you need a pressure dew point, the pressure of your system affects what your dew point is going to be. But mostly we're concerned with flow rates. So you definitely want enough flow rate to get appropriate sampling on most types of media. So yeah, we're talking mostly about flow rates and volumes, and a little bit less about pressure.
Okay, that's clear. Rebecca, what's the usual air class for packaging high hygiene air use?
So that's kind of up to your risk analysis. I can tell you some of the more common ones I see for high hygiene. 222 is a fairly common one for more demanding or product contact applications. You guys are probably mostly food, but if you get into sterile or sanitation settings like medical device or pharma, we see a lot of 121s. But it kind of depends on what are the tolerances of your product, what's going to cause spoilage in your product, and what's going to potentially cause harm to your customer. I definitely say lower particles and lower oil are very important for high hygiene. Really, really strict hygiene applications tend to go with a class 1 or even a very strict class 0 for oil contaminations. Particles can be 2 to 1 in a lot of these cases, and then depending on whether or not there's some kind of spoilage or desiccation that happens with your product, any number of water classes might be appropriate. So just keep. Yep.
Okay. Stephen's asking a question about food grade oils, but I think you've mentioned that it is good practice to have food grade oil if possible. Teresa asking about what possible pathogens are found in compressed air.
So, that kind of depends. You go back, and I don't know how many of y'all are familiar with Bluebell, but they had a huge problem with listeria all throughout their facility. And I don't know how much of it was actually in their compressed air system, but it was definitely a lot of things that were driven by compressed air were contaminated with listeria. As far as possible pathogens, it kind of depends on what products you're working with, what grows in those products. So if you're working with a lot of starchy type things, you'll probably see a fair amount of yeast and fungus in those kinds of settings. And a lot of that's going to depend on your pre-filtration and post-filtration. If you're working with dairy, you got a lot of opportunity for Salmonella, Shigella, Listeria in particular. You're working with poultry, Salmonella is going to be your biggest thing to look out for. And just keep in mind that your air system is going to be recycling the air in whatever building it's located. So if your compressed air system is close to production areas, you could be recycling whatever potential pathogens exist in your facility back into your air system.
Okay, great. Thomas is talking about aluminum, aluminium, as we say. Um, you said before, yeah, it's the deluxe thing, but what's the second choice then? What's the next best choice to aluminium?
So aluminum's fairly common. There's a couple of really interesting products out on the market right now that use kind of these hybrid compression fittings, like twisting compression fittings, threaded compression fittings with aluminum setups. They come modular. They're easy to put together. They tend to be sanitation coated, which is nice. And aluminum, pretty good material for these things. Just keep in mind those transitions that you need to make for your point of use or your sampling point. Aluminum is interesting in that it does exhibit corrosion, but the corrosion is of a nature where it forms a very, very thin layer, and that corrosion protects against further corrosion. The downside of it is if you've got a particularly dynamic system, one that's prone to a lot of vibrational modes, you can, on occasion, break that corrosion off, and it can cause problems further down the line in the form of small particulates. But aluminum tends to be a fairly solid material, but just keep in mind, your point of use filtration as well. So.
Okay, thanks. Jenny, bit of a long one, but I've got to read it out for future YouTube viewers who won't be able to see the questions. Is there any standard out there that state the sampling time or sample volume required for micro testing? I don't remember seeing any. So we have contractors doing the sampling for us, and I don't think the sampling time they do is more than a minute.
So that kind of depends on what you're looking for. If you're doing quantitative sampling, if you need colony forming units, there's no set standard that I'm aware of, but you want to achieve about a cubic meter. That way you can say for sure, I have these microbes in 1 cubic meter of air. It's harder to extrapolate micro results than it is other results. If what you need is qualitative, if you're looking for just pathogen growth in general, or looking for specific pathogens, sampling time is less important in that case. It'd still be nice to say, okay, well, we sampled for a cubic meter, but less relevant because you're not making a count per cubic meter now, right? So it kind of depends on what you're looking for. If what you're looking for is quantitative, there's not, I don't know that it's a standard per se, but the accepted amount is a cubic meter.
Great. And Pretty, do you have any idea about the sampling frequency? Would sampling quarterly be good enough?
I mean, that's up to your risk analysis. So if you've got a high demand system and you need to meet very, very strict requirements, more frequent sampling would be a good idea. If you've got less strict requirements and you're using it for indirect contact or driving machinery, less frequent sampling would probably be more appropriate. Quarterly tends to be the most frequent that I see, even in the most strict situations. I think I've got maybe a couple medical device people that do it monthly, but quarterly tends to be the most strict that I see. So hopefully that'll answer your question.
Okay, thanks, Matt. Simona, I would like to know what are the limits for micro test for compressed air and ambient air.
So funny thing about ISO 8573, there's no, if you remember going back to that chart slide, there's no mention of what an appropriate class is for a given CFU count. So the limits are kind of really up to you. It's part of your risk analysis. As far as ambient air, if you're doing environmental testing, I'm less well versed in the environmental side of things, but most of the time, you want it to be fairly low. It also depends on your application. Is your product something that microbes grow easily in? So if it's something like bread or bread dough or liquid dairy, you definitely want much lower limits than you would if you were packaging potato chips, which have a lot of oil and salt that make it harder for microbes to grow.
Okay. Well, bang, that's 1 hour. and I think Tori and Nikki and Ruby from Trace Analytics, your cohorts, have been mopping up some of the questions in the sidebar. So I think, unless there's any more final questions, we'll sort of say we've been successful in meeting our deadline in terms of time. Lots of great information. I know it's been your first webinar, and it's been a good experience from our point of view. Have you enjoyed it, Matt?
Yeah, it actually, I think, went at least better than I expected.
Yeah, oh, well, it always is. They're quite a friendly crowd, and there's always lots of questions and lots of interest. So appreciate your time today, Matt, and I hope to see you on another webinar with us in the near future.
All right. Thank you very much, Simon. It's been a pleasure.
Cheers. Thank you. Right, ladies and gents, that was Matt DeVay, Quality Assurance Director from Trace Analytics, LLC. Super presentation. We will send you the recording. We will also send you the slide deck, and we will send you also the certificate. I've loaded the certificate in the sidebar. You can download it now if you want to grab that. Please, it's a PNG. You've either got to print it and sign it yourself, or you've got to open it in an image editing software and then type your name and then print it. We can't personalize them, sorry, there's just too many to do. Just as a final thing, if you are not familiar, this is the 92nd webinar, Food Safety Fridays, so there is a huge archive. I've put the link in the sidebar, and some of those from Trace Analytics, and lots of other subjects, a myriad of subjects and presenters, and they'll keep you going for days and weeks, no doubt. Nice to have you with us today. Thanks for your attendance. Thanks for joining in and making it such an engaging webinar. Enjoy the rest of your day. It's Friday, and have a lovely weekend, and we'll see you on the next webinar. Take care. Thank you.